So I'll tell you about the company. We'll start with reviewing the company history, where we're coming from, and then I'll talk about Goya and later on Gaudi. At the end, I can take questions, or if you feel the need to ask during, feel free to raise your hand and we can address it. Okay? So who's Habana? Habana believes that for AI, there's a place for a new category of processing that we call AI processors. That will take its place alongside CPU and GPU. And I'll show you the reason why we need such a category. First, a short background of the company. The company was founded in Israel in 2016. Company is focused purely on designing AI processor for both inference and training. The design center are in Israel and also evolved into Europe for software. We have 2 business and customer support offices in San Jose, California, and here in Beijing. We are backed by prominent investors and entrepreneurs that started multiple successful companies. The company is well-financed, raised until now $120 million. The latest round that was done in November of last year, we raised 75, and this one was actually led by Intel Capital and joined by several others. We started by launching the Goya inference processor in September of last year. As I mentioned this morning, Goya has set a record on performance. And even now, 9 months later, Goya is still the performance leader. What you see here is comparison on the ResNet 50 benchmark in throughput of images per second. But we also overlaid here latency and power efficiency. And we are comparing to the latest GPU that is the T4 that is meant for inferencing, as well as a dual socket CPU. So you see that Goya outperforms the nearest competitor by over 3 times on throughput of images per second. And at the same time, we also offer much better power efficiency and much lower latency. So you see on several aspects, several metrics, Goya offers a superior performance. And as I mentioned this morning, the reason why we're able to achieve that is because of the architecture. Habana's engineer created a ground-up design that is optimal for processing AI. And that's an example of what you can do when you create an architecture with a focus on AI and not necessarily carry over architectures from other applications. This comparison I shown this morning, done by microprocessor report, Lily had to use log scale to compare them, right? 15,000 next to 1,000 is pretty hard to do on a linear scale. So it's over 3 times back then. It's still over 3 times now. And how you can use that? Like, what do you do with all this throughput? So I chose here to show that in the same way that Nvidia chose to show how V100 could replace many more CPU servers. So in the data center case, if you need to deliver 45,000 images per second, Nvidia pointed out that rather than spending $3 million on 169 CPU, buying 8 V100 could be more effective. We agree that we need more effective solution, but we suggest that data centers that predominantly use CPUs for inference would be better off on using just 3 Goya cards to deliver this throughput. And you'll get this throughput. You'll get also real-time latency if you need that. So as I mentioned, the achievement is rooted in architecture. It's not about a more advanced process technology. We actually use 16 nanometer, which is actually older than what you can find with CPUs and GPUs today. And what we've done is that we assembled a multidisciplinary team. Habana comes with a very deep background of engineers in CPU, DSP, networking system, software, machine learning research. You put together all these disciplines, and we come up with a ground-up design of a tensor processor core that we call TPC. We came up with our own instruction set. We came up with our own LLVM-based compiler, complete development environment. We added other IPs inside the chip, including a general matrix math engine, a very special way of managing memory efficiently, and using actually not too expensive memory technology. DDR4 is not the most advanced. We are still providing much higher performance. Now, performance is not just throughput. There are also other aspects to performance that could be important for different applications. So what I'm here to dive in with you is to review why performance is actually could be a combination of throughput with low latency at low batch size. So that's kind of a mouthful, right? So I'll go over it in detail. So let's look at the ResNet 50 performance again, but this time, instead of looking just at the maximum throughput, let's evaluate what would be the throughput using different scenarios. And the batch is really the industry term of how many data samples are you giving at once to the processor when you measure the performance, right? And ideally, at least in some application, they would rather use a batch size of 1. So imagine you want to give the processor one image, and you want to get the result as soon as you can. Where is it important? I will show you a few cases where it's important. But some processors that are not made for AI necessarily getting to their maximum throughput only when you use very large batch size. It means that they require you to assemble many, many pieces of data and then give it in a whole group, right? And then wait for the whole group to come back with results in order to get the maximal throughput. And one of the things that are unique with Goya is that not only does it provide the highest throughput, but it's able to achieve it while using a relatively small batch size. Batch size of 10 is all you need in order to get to the maximum throughput. And it gives you around 1 millisecond of latency, which is very low. And if your application requires even lower latency and using a batch size of 1, we get to incredible latency and still have very decent throughput. So let's explore where is it useful. If we look at data centers, one of the questions data centers have is that if they buy hardware and install it in the data center, how well can they use it? Can they use it on more than one thing at a time? If they have to use it only on one thing, it means that the cost need to be burdened by this one application. However, if they have different use cases, different customers, it would be very attractive if they could share it. And if you have an engine that has not only high throughput, but the ability to give you low latency and doesn't force you to use a very large batch, you can start thinking on how you could use the same AI processor card for multiple customers and be able to guarantee a service level agreement with the ones that care about it. So maybe some applications care about latency and the other just care about throughput. So if you employ a simple time division multiplexing on the system software level, now you could talk about using the same hardware for multiple customers at the same time. So the economy of reusing the hardware comes into play. And this advantage will mean for data centers that it just lowers the operational expenses. So you see with Goya, you get several advantages that are added to each other. You get incredible throughput, you get low power, and because of the latency and the ability to handle multiple topology and switch between them very quickly, you can also use the hardware in ways that will actually save you a lot of cost. Now, this is a case of data center. There are other cases. For example, if you are going to use inference in an autonomous vehicle, and in an autonomous vehicle, you use lots of sensory data. You need a neural network that can help you plan the drive path. This is an application where latency is actually very important, right? You don't do it overnight. You need to do it in real time. So to do it in real time, you want the inference engine to use a very low batch size because you cannot afford to accumulate 128 samples, right, to get to the maximum throughput like the T4 GPU asks you to do, right? So there are some applications where latency is not important, some applications that it is important. What we are showing you here is an engine that is architected optimally for AI, and now you get all these flexibilities that are added on the inherent advantage in throughput that I already shown you. Software is absolutely critical, right? If you come up with a processor as good as it is, but your customers are having a hard time to use that, then forget it, right? You can't use it. So when we designed the Goya inference processor, we also brought in a team with experience of designing and delivering 20 years of history of DSPs, processors, et cetera. And we used that in order to come with a software stack that makes it easy for our customers to migrate from less efficient solutions to Goya. And what I'll do now, I'll go over the software stack in high level with you. So if we look at the field of AI, all of you know that neural network frameworks, deep learning frameworks were developed in order to abstract the usage of engines, right? If in the past many people used lower level languages like CUDA or C, most people want to program in Python and get to extra productivity, right? So there's a trend. Now, if you're going to introduce an inference engine, you need to connect with that trend. So our software stack that's called Synapse AI interfaces to some of the most popular frameworks directly. So if you trained a model on whatever training platform you use, you typically get a model that was trained in floating point. And if you want to use an inference engine, you need a software stack that will take that trained model that you worked very hard to achieve your goal, and now compile it to the target hardware so that it will be executed efficiently and accurately. So the process that our software stack goes through for doing that is that we take your trained model. You also give the software example data. We turned your model into an internal representation. That's what the graph compiler does here. And we are doing a process that we call quantization that allows you to reduce the data types from floating point to a combination of floating point and integers, as much as integers as possible, while allowing you to control the accuracy. In that process, the graph compiler that is aware of the architecture of the hardware is auto-generating the code that would run on the target hardware to generate what will be what we call an execution plan that we call a recipe. That recipe represents an execution plan for that target model that you have. And finally, the runtime environment allows you the control of which of these recipes you're going to activate. So you can preload many recipes to the hardware that has onboard DRAM. They can be resident on the hardware, and the runtime allows our customer to control which one of them to execute. Now, on top of this whole flow, which is really critical to enable you to have that experience of working at the neural network framework and generating the code that you need running, we also are aware that, especially for some customers who invested a lot of time in customizing their neural network to run efficiently on GPUs or others, some of these customers created custom layers, created custom kernels, right, that map to those layers to get their inference done efficiently. So anticipating that, Habana did two things. First of all, we obviously developed a rich kernel library, 600 kernel libraries supporting probably most of the things that are actually useful, right? But we also anticipated that some customers may want to customize the implementation because they already invested in that before. So we offer our customers an ability to also generate quite easily custom kernels of their own, so they can inject their own secret sauce or definitely maintain investment they've done on their inference models on other architectures. So the graph compiler would discover both the Habana library plus if a customer generated the library. And in the past year, ever since we introduced Goya, we have actually helped customers to migrate even custom layer models to our hardware, and we train multiple customers on how to do that. So this work that was done on Goya obviously laid the groundwork for us to introduce Gaudi, which I'll talk later on. And one more important point is that Goya doesn't force you to do training on specific targets. You can train your model on anything, right? So you can train it on a CPU, a GPU, a TPU, and in the future on Gaudi, but we will not force you to use Gaudi to use Goya, right? These are two independent things. We let the customer have the flexibility to use whatever is good for them. So part of the software infrastructure and tools include, of course, the Synapse AI, which include the high-level components of graph compiler and runtime. Probably most of the users that just want to work in the framework and push a few buttons to make it run will work just with these. The more expert users who want to do custom kernel development are provided with a complete toolchain. This toolchain includes our own LLVM-based compiler, assembler, debugger, a very unique performance profiling, and this is what we've done supporting customers, so if they want to, they can definitely do that. Our software today supports TensorFlow, MXNet, Onyx. Onyx is a neural network exchange format, so you can actually use that to move topologies between other frameworks as well, and we're expanding this over time. One of the examples of Goya's maturity, a few examples are mentioned here. Habana will not talk about which customers are using hardware, et cetera, because we respect customer confidentiality. But there was one thing that Facebook did publicly, which is announce that for their Glow machine learning compiler, they actually selected Habana as the first AI processor that they used as a backend to Glow, the machine learning compiler. If you search for Goya and Glow, you'll probably see that post by Facebook. So that's a testament of someone has actually decided that it's worthwhile to do that. Someone is Facebook. We also upstreamed our kernel mode driver last year. So if today you're going to download the Linux distribution from kernel 5.1, we are in the official Linux distro. Obviously, the hardware was qualified, passed PCI certification, etc. So to summarize, what we feel is that the inference market really demands better solutions, right? And the criteria for a much better processor include throughput, latency, power efficiency, size, and cost. These are all really needed to democratize AI, to lower the cost of AI substantially, and really help people use that technology. And we believe that a best-in-class solution has to be custom built for AI, right? There's only a limit to what level of efficiency you can get from architectures that were meant to do sequential processing like CPUs or graphic rendering. You can do many things, but if you really want to do something optimal, you better use a processor that was custom built for AI, and that processor needs to be absolutely software programmable. It cannot be hardwired. It needs to give you all the flexibility that you need to be truly called a processor. And we believe that we have shown that for the inference market, whether it's CPU or GPU, Goya is the ideal evolution. We have shown key benchmarks. On our website, you can see also other benchmarks. You can download the white paper. In all the important metrics, we see order of magnitude improvement that from the end customer, it means lowering their operational expenses, lowering the power consumption that they use. Data center have a limit to how much power they can drag. And also giving them other capabilities that are important for different applications like real-time latency. So that's the presentation about Goya. And next, I'll talk about Gaudi. And this is actually most of my presentation. So Gaudi is Habana's second product line. Habana decided early on, even though we are not a huge company, we decided early on to pick up the challenge of providing two product lines, not one. And we figured that we have to do that because if we really want to be a market leader in this field of AI, we cannot expect customers to compromise by using the same processor for both inference and training. There are enough differences between inference and training that you actually have to do dedicated processor for both. And that's exactly what we've done. And Gaudi, we are showing, is again, similar to Goya, demonstrating it to be the highest performance AI training processor. So on the ResNet 50 benchmark, this time training, we are delivering the highest throughput for a single processor. And if you connect the dots from what I talked about, the relationship with throughput and batch size, it is no accident that Gaudi can deliver high throughput even at a small batch size. Though for training, the importance of that is coming from a different direction. And that's because training systems are not sensitive to latency. Training system, what you care about is to accelerate your training. And the way you do that is that unlike inference, that you take a sample and you get the result and it's running on one processor, in training you actually employ, in most cases, many processors to work together. And you use different techniques to train your neural network framework. One of the most common methods is called data parallel training. And in data parallel training, what you generally do, and this is like 95% of the market is using that, is that let's say you build a training farm of X GPUs, you take the mini batch iteration, you divide the data across the GPUs or processors that you have, because you hope that you can linearly accelerate the training time, right? And this would work only if the architecture of that processor will allow you to do that. And one of the issues with some architecture is that if you do that, they are losing efficiency. So the throughput goes down if you cut down the batch size. And you can go to some of the market leaders and look at their website and ask, see for yourself, what is the throughput for different batch sizes? You'll observe that it is losing efficiency. So to show you what kind of throughput you can get from Gaudi, I'm showing this graph, which is looking at the ResNet 50 benchmark throughput, comparing Gaudi versus the V100 GPU, but this time comparing it for a full system, comparing it at scale. So what do we see in this graph? This graph is the Gaudi throughput. I'll show the comparison in a second. But what you'll observe is that as you increase the number of Gaudis, the throughput goes up accordingly, almost with near linear scaling. And if you want to compare it to the market leader today in training, which is the V100 GPU, you will observe the following. The x-axis here is the number of GPUs or Gaudis that you're going to use in a single system. The y-axis is the throughput, but this time for the entire system, not for a single processor. And that's where you get a sense of how scalable is the architecture in allowing you to accelerate training if you're going to build a bigger system. And one of the opportunities here is that not only Gaudi outperforms V100 in all system sizes, the advantage with Gaudi is actually even bigger when you go to a larger system. And that's directly because of Gaudi's unique ability to maintain high throughput even when you cut down the batch size. You have to cut it down if you're going to scale your system. The results that we show here on the green line are based on NVIDIA's submission to MLPerf. If you go to mlperf.org/results and you look at the closed division training time, you can see for the ResNet 50 what is the amount of time until the benchmark converges to the target accuracy. And if you look at the definition of the benchmark, 72 epochs, X number of frames, you can deduce directly what is the actual throughput that you really get from that system of V100s. And you can see that the advantage goes to the point that for a system of 640, we provide an acceleration of nearly 4x in the throughput of the entire system. So many of you will be using different topologies, of course, but the benchmark goal is to give you an indication. And the insight here is that with Gaudi, similar to how we show it with Goya, when you have an architecture that's architected for AI, and it's architected correctly, it's more scalable. And in the case of training, the meaning of that is that if you invest in scaling your hardware, you get a much better return on investment by getting actually throughput that is near linear in scaling. And that's not the situation today based on the official submissions of V100 results by NVIDIA. So we talked about performance at scale. Now is the second piece that we feel is really important with Gaudi. And that piece is something that we understood years back when we started Design Gaudi, which is that scaling AI processing and the challenges involved in having those processors collaborate together in that training is really a networking challenge, right? So what is better than using the best networking technology to collaborate between these processors? And that best technology is called RoCE, RDMA over Converged Ethernet. So what we've done is that we've integrated those RoCE engine on the processor chip itself. And Gaudi is the only AI processor who did that. And what we have showcased here, and you can go to our booth and see that, you can see a fantastic networking bandwidth of 10 times 100 gigabit Ethernet interfaces integrated on the processor chip itself. So what this means for data centers or people who build training farms is that they can now use standard Ethernet as their strategy for scaling AI and avoid any proprietary interface as other solutions require. And we are not the only one that are saying that RoCE is a good technology for scaling AI. If some of you have seen Nvidia CEO presentation, Nvidia CEO, just before he invited the Mellanox CEO on stage, explained that RoCE is a good way to improve the ROI on adding more and more servers. So Habana agrees. And now let's evaluate the difference between Habana's solution and the combination of the Nvidia solution with Mellanox. So on the left side is the Volta architecture. And as in the next few slides, I'll also talk about the DGX and the system. But if you kind of ask yourself, OK, how do we, like if you're going today to buy V100, how can you get RoCE used as a scale-out interface? You'll observe that you'll need to have the V100 GPU connected to a PCI switch, connected to a NIC of 1 port of 100 gigabit RDMA. And with Gaudi, you get it in a single chip with 10 times the throughput. So what hardware do we provide and how do you use that? Let's now dive a little bit deeper, right? So on the left side, you can see one of the form factors that we provide for Gaudi. There's also a PCIe card. This form factor is called OCP OAM. If you're not familiar with that, OCP is the Open Compute Project. And one of the important initiatives of that industry standard is to actually create a standard for accelerators. So OAM is the OCP accelerator module spec. And we are very proud to work with the OCP and contribute. And Gaudi is probably going to be the very first AI processor that is provided in this standard form factor. And the Gaudi chip includes on the chip, in an open package that you can see in our booth, 4 HBM2 memories, providing 32 gigabytes of memory, incredible memory bandwidth of 1 terabyte per second, ECC protected. And as I mentioned, these Ethernet networking, these RDMA engines, are inside the chip, and the actual card interface includes very high-speed serializers. Those serializers are 56 gigabit per second PAM4 SerDes that can be configured as 10 ports of 100 gigabit Ethernet or 20 ports of 50, or any combination in between. And on top of that, there's a PCIe port that is dedicated for host interface. Now, if you go to our booth, you also see a system that we called HLS1 that we also provide our customers if they wish to do that. Obviously, customers that want to design their own system can simply buy mezzanine cards and design many types of configurations, right? And some of them may be finding that HLS1 is relevant to their system. So I'll now talk a bit more detail on how you use that. So let's look at HLS1. 1 second. Let's look at the inside, right? So HLS1 includes 8 of those Gaudi mezzanine cards that I shown before. What you see on the front are 2 PCIe switches, right, that together provide 4 ports of by 16 PCIe. So that's for host management. And some of the Ethernet ports are exposed for scaling up the solution. 24 ports of 100 gigabit Ethernet. So this box does not include the CPU, right? If you compare to DGX1 as an example, DGX1 has integrated CPU. We chose not to do that. And the reason is because talking to customers, we realized that there are different applications, different topologies, different ratios of CPU to AI processing that's actually required. So we decided not to integrate the CPU and let our customer choose the CPU that's right for their application and connect that CPU box to HLS1 via PCIe cables. What you see here are mini SAS HD. And that's a connector. If you go to the Open Compute project and you see what Facebook contributed, you can follow these steps. You can saw a server that has those PCIe retimer cards and hook it up via cables. So you can build the whole rack. Now you can scale. And this is where the true power of Gaudi really is shown. You can choose the CPU that you want, connect it. In this example, it's a 1U CPU that you connect with 2 PCIe cables. And that forms your basic server. If you need more acceleration, more Gaudis, you simply stack up those boxes. And by using a standard 100 gigabit Ethernet switch from your favorite supplier, you just hook it up using cables, and you're done. Now you have a full system that meets your needs. And you have scaled it using standard interface only. There was no proprietary interface here. So let's compare similar system by Nvidia based on V100 to the HLS1. And I want to emphasize that our customers can actually design many types of systems based on the building blocks that we're giving them. So HLS1 is just one example. So how do we compare these two boxes? If we look at V100, V100 is the GPU with proprietary interface called NVLink. In contrast, Gaudi has integrated the compute with the networking, and we are using a standard interface. Gaudi has integrated RDMA engines on chip, but the physical interface is a standard Ethernet. And this same technology is used for scaling at any size in any network size. On the other hand, with the proprietary NVLink, it's a proprietary system interface. It does not extend beyond the box, and even inside the box, it's a blocking internal interconnect. The interconnect that we designed in HLS1, we simply took out of the 10 ports of 100 gig, we took 3 ports as a way to scale up, and the other 7 are just connecting directly. So our high-speed serializer are able to support interconnect inside the box. So imagine you get a RoCE network inside the box so that Gaudis can collaborate with each other. And the same networking technology can be extended with any number of Ethernet switches across the data center. So that's one of the two powers here. And if we compare like throughputs, the Nvidia needed to go through PCIe switches to get to 4 NICs to give you 400 ports of 100 gig. You get 24 just by this box. The other aspect that is, I think, more understood by people who actually used GPU training systems is that there's an actual issue when you combine over PCIe both the management traffic and the scale-up traffic. Okay, it's a bottleneck by itself. And we chose to separate those out. So we have a PCIe Gen 4 switches that are used just for the communication of Gaudi to the host CPU. Of course, the RDMA engine inside can also direct themselves over PCI if you choose so. But why would you do that? You have Ethernet, specifically designed as the best technology to let them communicate. So there's another aspect of performance improvement by separating the host interface from the scale-out interface. There's also a second standard form factor that we provide our customers, and you can see it in the booth today, which is a standard dual-slot PCI card. If you plug the V100 PCI card into an existing server, you can swap it out and plug in a Gaudi standard PCI card with one additional addition that we support networking interface on it. Okay, software stack is similar to what you see with Goya, but adding more features to the software, including just-in-time compilation as well as ahead-of-time compilation. Now I'll walk you through several examples of different scale-out that you can build. This is an example of a 16 Gaudi system. This one is using 20 ports of 50. So you can use the all-to-all interconnect with 50 gigabit Ethernet and still have 32 ports. One of the properties of training is that data parallelism is a way to distribute the data that I explained before. There's another method of training which is used for very high performance system that have gigantic models in which you split the model across processors. So those two different approaches pose different challenges to scaling AI training system. And what I'll show you is that with the Gaudi integration of Ethernet, you can design systems that fit your needs with much better flexibility that you had until now. So data parallel training allows you to do reduction of the weight updates. So this means that you have the ability to construct systems that take advantage of this property, where the bandwidth can be reduced as you build larger systems. So here's an example of how you can build a training system with full throughput using Ethernet switches in layers. In this example, there's 1,000 Gaudi processors you can build by simply using Ethernet switches and connect those in layers and still getting the full throughput of training in data parallel construct. Because Ethernet is the networking technology that's familiar to everyone, we have now unlocked the potential of scaling training very easily with the technology that's familiar to everyone. So that's why it's key to integrate it inside the AI processor. Now, there's also another family of training algorithm that's called model parallel. As I mentioned, model parallel is a technique where you have a model that you actually could partition the model calculation, forward and backward propagation between accelerators. This poses much tougher bandwidth requirement. You need much more bandwidth, and you need it in low latency for the training to actually accelerate. So because we integrated Ethernet interfaces on the chip itself, you can now take the HLS1 and simply take all the ports out as a scale out. So a 3U box like that can expose 20 connectors, each of them carrying 400 gig. And now you can have gigantic memory bandwidths. So let me show you how you can use that. If you look at DGX2, which is the most advanced training box by Nvidia, the DGX2 is using NVLink. However, NVLink is not scalable outside of the box. So for people who bought DGX2, they know that if they try to scale beyond the box, they hit a bandwidth wall. It's really not scalable with meaningful bandwidths unless the model can fit in the box. But with Gaudi, when you introduce Ethernet switches that you put in parallel, if you take the box I shown you in the previous slide, you can enable massive bandwidths. You can do model parallel across 128 Gaudis, not 16, using a standard Ethernet switch that you can source from 3-4 vendors today. And there are bigger switches coming soon. So what I'm showing here is that we are unlocking a potential to tackle models that today you cannot solve, right, unless you have this kind of architecture. You can build combination of architecture. You can have a switch inside the base unit that can enable lots of bandwidth inside the box and can be built hierarchies on top of that. So you let your imagination go free. We enable our customers to create systems that solve their problems using standard interfaces. So if you look at the Habana lineup of products, you have 2 processor cards, both of them standard compliant, right, standard form factor. You can plug this one into existing server and use Ethernet ports, right, to form a ring or connect to a switch if you want to build a bigger system. You can either design your own chassis if you want to use the mezzanine or buy HLS1. And to summarize the value proposition of Habana Gaudi, we summarize it on two components. One is that the base architecture is just more efficient. You get record throughput and power efficiency. Advantage of this is obvious, right? You can accelerate your training, you can lower your power consumption, you get much bigger headroom. The second one is even more strategic, because by integrating RoCE on chip, we enable our customer to scale AI like it was never done before. And it allows them to build scale of systems that can handle problems from small ones to more complex, data parallel, model parallel, anything in between. And one of the things that's most important about this is that we allow data center to avoid depending on any proprietary interface. And this is really important. If a data center can avoid relying on a proprietary interface, they avoid locking themselves to any supplier. And there's no better than Ethernet networking to allow them to have an ecosystem of suppliers. So in the future, if they find a better AI processor, they can replace the processor vendor and still keep the infrastructure. And that's incredibly important for the strategy on how to scale AI system. And with Gaudi, you can realize all these benefits.